15.1 Vector Fields. Let D be a region in three-dimensional space. A vector field is a function f that assigns a vector to each point in D. For example, a velocity field could model the motion of air particles in a breeze at a single moment in time. Individual vectors indicate direction of motion. The length of each vector indicates speed. Areas of study that use fields include looking at wind patterns, circulation, gravitational, magnetic and electrical force fields, stresses and strains in buildings, chemical pollutants, human migration, current, flow of air around an airplane wing, electrical force fields. So a vector in two-dimensional space will be written GH in general. And keep in mind that G and H are both defined on the region in two-dimensional space. The vector field is continuous or differentiable on the region if its components are. We're going to start with a simple vector field called a radial vector field. At each point xy, there is a vector xy. The tail of the vector is at the point xy with length square root of x squared plus y squared. Notice that the lengths of the vectors increase as you move away from the origin. The vector at the point 1, 1/2 has the length and direction of the vector going from 0 to the point 1, 1/2. However, the vector will start at the point 1, 1/2. If the f represents the velocity of a fluid, the graph here shows how a small object, such as a cork, might move through the fluid. At every point of the fluid, the cork moves in the direction of the arrow at that point with a speed equal to the length of the arrow. For this reason, vector fields are sometimes called flows. Let's look at some other vector fields. The shear vector field. Here's another one that's pretty interesting, the channel flow field. And here's one that you're going to see a lot, the rotation vector field. At the point 2, 1, we place the vector -1, 2. Notice the relationship between the radial vector field and the rotational vector field. Let's go back to the looking at the radial vector field, and I want to generalize this idea of the radial vector field. Let R be the vector xy. Then the general radial field in two-dimensional space is going to be R divided by the magnitude of R raised to the p power. Now, if I break up the vector field so that it looks like this, the first piece is a unit vector giving direction only. The second piece is the inverse of the magnitude of the vector r raised to the p minus 1 power. That's a scalar value. If p equals 3, then we have what's called the inverse square radial field. And it's a pretty important radial field as it describes central forces such as gravitational force between point masses or electrostatic force between charges, both of which obey the inverse square law. Let's look at some various values of p. Here's what the radial vector field looks like for p equals 0.5, so p is less than 1. Lengths of vectors are going to increase with the distance from the origin. And then in the next one, I'm going to increase p just a little bit, but still have it less than 1. And then if p equals 1, then I've got, they're all unit vectors. And then p equals 3, that's the inverse square radial field we were just talking about. The really long vectors are the ones that are very, very close to the origin. Let's look at the circle x squared plus y squared equals a squared. And we can view that curve as a level curve. So the gradient of the level curve is normal to the curve. We know that from a previous chapter. So the vector xy will be normal to the curve. Now, since the vector n, which is xy, and t, which is negative yx, since their dot product is 0, we know that n is normal and t is therefore tangential. Well, this is interesting. So our normal vectors are the radial vector field with p equals 1, and the rotation vector field gives the unit tangent vector to the curve at each point. All right, let's move on to three-dimensional space. A vector field in three-dimensional space is usually written FGH. Now, each component is a function of three-dimensional space. And as before, the vector field is continuous or differentiable if the components are. We have the general radial field. The only difference now is that r is equal to x, y, z. Here's an interesting vector field in three-dimensional space, x, y, e to the negative z. Notice that the first two components of this field are like the radial field. The third component, notice that it will always be positive. Now, as z increases, then e to the negative z gets closer and closer to 0. And so the vector field starts flattening out and starts to look like the two-dimensional radial vector field. Here's one that might mimic, say, blood in a blood vessel. Notice that the first two components of this field are 0, and that the z component is always positive. So in this case, the vectors point straight up with a maximum length of 1 on the z-axis. And the length of the vectors will decrease to a length of 0 on the cylinder of radius 1. Let's go back to this notion of gradients. Let phi be a differentiable function in two-dimensional space, and let the graph represent level curves of the surface z equals phi. Now, at each point AB on a level curve, the gradient is orthogonal to the curve. Now, that's old information. Let's tie that into vector fields. Given phi, we can now define a vector field whose f equals the gradient of phi, whose vectors point in a direction orthogonal to the level curves of phi. This is called a gradient field, and phi is the potential function for the gradient field. Here's an example. Let phi be the temperature on a circular plate. The graph shows some of the level curves for phi. let's find the gradient field for phi. The gradient field is going to be negative 2x, negative 2y, a negative radial field. Notice that the length of the vectors decrease as we get closer to the origin. Now recall that the gradient points in the direction of greatest increase, and in this case that is in the direction of the greatest heat increase. Take care, and I'll see you in the next section.